This RF board passed every single design review with flying colors. But on its very first try in the lab, it completely failed the EMI test. Here's the crazy part. There was absolutely nothing wrong with the components. On paper, the schematic was perfect. But in reality, the system suffered from massive RF degradation and unstable signals. The real culprit was hidden deep within the PCB layout. In this video, we're going step by step through the 3 hidden layout mistakes that tanked this design, and how we fixed them to pass compliance without changing a single physical component. When we first looked at this board, everything seemed normal. But high-frequency signals do not forgive layout mistakes. We uncovered 3 major flaws ruining the RF performance. First, unintended coupling. Sensitive RF tracks were placed way too close to high-speed digital lines. Because of that, digital noise easily coupled straight into the RF paths, destroying the antenna's performance. In high-frequency design, even a few millimeters of bad spacing ruins everything. Second, excessive trace length. Some RF paths were just too long. At high frequencies, long tracks start acting like accidental antennas, radiating signal energy right into the air. This kills your performance and spikes your EMI. Third, and this was the biggest issue, discontinuity of reference planes. Too many designers focus only on the forward signal, forgetting that the return current matters just as much. On this board, the ground plane beneath the RF traces was broken up. Since the return current couldn't take the shortest path back, it was forced to loop all the way around the board. That massive loop caused impedance mismatches, signal reflections, and a nightmare of radiated emissions. The failure wasn't the schematic. It was purely how the circuit was physically laid out. So, what was the fix? We didn't need expensive shielding, and we didn't swap any parts. We just fixed the layout in 3 steps. Step 1. We rebuilt the ground structure. We put a fully continuous ground plane directly beneath the RF traces, so the return current could take the shortest path possible. Step 2. We added stitching vias at key points across the board. This locked down ground continuity and stopped electromagnetic leakage in its tracks. Step 3. We optimized the critical paths. We shortened the RF traces, cut out unnecessary vias, and crammed the decoupling capacitors as close to the power pins as humanly possible to kill noise at the source. The result? It worked perfectly. Conducted and radiated noise plummeted. On the very next EMI test, the board passed with flying colors, with 0 hardware changes. Failing a compliance test is a massive bottleneck. Fixing a layout mistake after production costs a fortune compared to doing it right the first time. Success always comes down to the details: ground continuity, return paths, trace lengths, and via placement. If you're working on RF, high-speed telecom, or 5G boards, and need your design to pass on the very first try, let the experts handle it. You can count on the HIGHPCB team for layout reviews, signal integrity optimization, and high-frequency manufacturing. Click the link in the description below to connect directly with our technical engineers. Don't forget to like and subscribe, and we'll see you in the next video.